you're given complex number 1 minus the square root of 3i to find the cube root of z and the natural logarithm of z. Pause the video and finish this off for me. Okay, have you finished? What did you get? Now remember that even though the question says the cube root, there will be three cube roots. Each will be separated by 1/3 of a complete revolution. Alright? There are 2 cube roots separated by half a revolution, which means separated by 180 degrees. 3 cube roots would be separated by 1/3 of a revolution, which would be 360/3 is 120 degrees, and so on and so forth. Alright. Now remember, to find the powers, well, the root is really a power, you know. When you raise a number to a half, you're finding the square root of the number. You raise a number to the power of 1/3, you're finding the cube root. Raise a number to the power of a quarter, you're finding the 4th root, and so on. So if you have x to the a over b, it's the b root of x raised to the a. Or you could find the root first, or here you find the root first and then the power. You could raise to the power first. So it's really x to the a, and then whatever you get, you find the b root of it, right? Same thing you'll get. So a, the top number, when you raise a number to a fraction, the top number is the power. The numerator is the power, the bottom number, the denominator is the root. Alright? You have to remember the Morris theorem. If z is equal to a plus, well, I like using j, but since they use I for this already, plus bi, then z to the n, well, it's going to be, you're going to change this to polar form. So z is going to be r cos theta plus I b sine theta. You have to remember that. Where r is going to be the root of a squared plus b squared, because remember, a is the horizontal or the real axis and b is along the vertical or the imaginary axis. So r would be the hypotenuse of a right angle triangle. Alright? Theta would be here. So theta is b over a. So theta, well, tan theta, I should say tan theta is opposite over adjacent, which will be over a. Alright? So remember that. You have to remember in order to do this. Okay. So z is 1 minus cube root of 3i. So z is equal to 1 minus cube root of 3i. Alright. Now, you need to find out what this looks like. You draw your circle. You have your x and your y axis. 1 means you move one place to the right. Minus, you go down. So the complex number will look like this. In fact, let me draw this circle larger. Get a larger circle. Let's look at these shapes. Alright, nice. So is 1 minus that. Okay, so we have our quadrants in the circle. All right. So from left to right is 1. And going down is the square root of 3. Square root of 3 is greater than 1. I want to draw it. Let me draw it. Make it look more like what it would look like to scale. Alright, so let me bring this a bit over more. Alright, so here, go down a bit more. Alright, so this is 1 and this is square root of 3. Good. Now, this is going to be the r, which is the magnitude of z. Or the angle, remember, angles are measured from the positive and an anti-clockwise direction. So we're going to have to find out what that angle is. Now, let's draw the triangle representing the square root of 3 and 1. Now, the magnitude of z is going to be the square root of 1 squared plus the square root of 3 squared, which is going to be what? Square root of 3 squared is 3, and then you plus 1, so that's going to be 1 plus 1. 3 plus 1 is 4. Square root of 4 is 2. Right. So the magnitude of the complex number is 2. You have a right angle triangle here. So you have your magnitude of z. Oh boy. Your magnitude of z is equal to 2. This angle now. Alright. Now if you find the angle that is right here, call it alpha. Tan alpha is going to be opposite over adjacent, square root of 3 over 1. So alpha is tan inverse of 3 over 1. Let me write it out here. So tan of that angle alpha is opposite square root of 3 over adjacent, which is 1. So alpha is the tan inverse of square root of 3. Well, square root of 3 over 1 is just square root of 3. What's the tan inverse of square root of 3? Let's get our calculator. Three. Where's the square root? Oh, I didn't remember there was no square root. But let me see something here. I want a square root. In this case, with using this calculator, I'm going to have to say 1 to the power of, open bracket, 1 over 2, close bracket, equal. Why these people have to make this calculator like this? No square root sign? Oh boy, I tell you. Alright, so, oh, this is in radian mode, this degree mode I want it in degrees, so let me clear the calculator screen. In fact, let me use the other calculator, because I don't know how it is that that calculator doesn't have a square root sign. Convenient. Oh boy. Alright. So, square root of 3 equals that. Okay. Now I want arctan. Is arctan they call tan inverse. Equal 60 degrees. So So it is 60 degrees here. This is 60. So going around here now would be 360 minus 60, which is 300 degrees. All right. So theta is 300 degrees. Okay. So now, in polar form, Z is equal to magnitude again 2 cos 300 plus I 2 sine 300. Okay, so that is the thing there, the complex number in polar form. Now the thing is, you want to find the square root. Remember now, by the Morse theorem. Did I write it down before? I didn't write it down, the Morse theorem, before. Or did I write it and erase it? Alright. If Z is equal to A cos theta plus I B sine theta, then Z to the n is equal to A to the n cos n theta plus I B to the n sine n theta. That's the Morse theorem. So now we have Z is equal to, why does 2 look like Z? Let me write it more like 2 with the curve up here. Good. So the cube root the first cube root will look like this. The cube root of Z, call it first, is going to be 2 to the 3. Oh, not to the 3, to the 1/3, because n would be 1/3. When you find the cube root of a number, is the same as raising the number to the 1/3. In fact, let me write it first like that, the first part of it. Z to the 1/3. Oh, I can just keep it like that for now. The cube root of Z, once I remember, is 2 to the 1/3 cos n theta, which is cos 1/3 times 300, theta is 300, plus I 2 to the 1/3 sine 1/3 by 300. Good. So the cube root of Z, the first, I'll just label it as the first to remember, is going to be, you can just write it as the cube root of 2 cos 1/3 of 300 is 100, right? Plus I cube root of 2 sine 1/3 of 300, it is 100. So that's what we have there. Now that's the first cube root. Let's find out what that would look like. What would that look like? Let me put this thing out here. Could expand it a bit. Now, the cube root of 2 sine 100. What's the cube root of 2? 2 raised to the power of open bracket 1 over 3 close bracket equal 1.26. Alright, so here, this thing jump up here. There is this the radius is equal to 1.26 then, which is the cube root of 2 sine 100. So here the angle is 100 degrees. So if you go towards this way, 100 degrees will be a little more than 90. So call it that. Alright. So it's cube root of z first. That's the first cube root of z. Right. The question did not ask you to draw it, but I just draw it for illustration. Now, the second cube root of z would be, now the separation, the cube roots are separated by 360 over 3, which is 120 degrees. They have the same magnitude. They all have the same magnitude. It's like a radius of the circle, same radius. Now, 120 degrees. So this would be same cube root of 2, but cos 100 plus 120 degrees plus I, same cube root of 2, sine 100 plus 120 degrees. Alright? So the second cube root would be cube root of 2 cos 220 plus I cube root of 2 sine 220. So 220 degrees would be about how much? Oh, by the way, guess what? I forgot, you know. Supposed to have a protractor here. We can measure our angles then, man. The protractor. Alright, so I said 100, so this would be 90. Let's flip it around. This looking at the middle part is that part we're going to have to measure. Or is the top part? I said 100 degrees. Oh, I can measure with this too. I can measure with this. Nice. Very nice. I can get my 100 accurately though, man. I was a little off, but close. 100 would be right there. Right. So 100 degrees would be there. See that? So this would not have been 100, my 100. I now have my 100 degrees. And then, what was the other angle again? 220. I want a 220 degree. So here now, 220 is 100. 220, oh, it would pass 180. It would pass 180. No, we'd have to go 20 more to pass 180. So if I should spin this around, 20 degrees here. Good. So I now have my 220 degrees. Good. I have my 220 degrees right there. So this would be cube root of z second. And then what is the third cube root of z now? We want cube root of z 3rd, the third. So this is the second and this is the third cube root of z. It's going to be cube root of 2 cos. The original was 100. So you add the second, which is 120, and then another 120 to it. You could very well say this is 100 plus 2 by 120. Alright? Plus I cube root of 2 sine 100 plus 2 times 120. So this is the cube root of 2 cos. 2 by 120 is 240, and then add 100 gives you 340 plus I cube root of 2 sine 340. See that? So 340 that's going to be 40, 50, 20 less than 360. So let's see where that gives us. Let me flatten out this and go. This would be 180, 70, 160. Alright, this would line up with 340. So the other angle would be right there. So it's a little bit off, but you see the center should be about here. No? I draw it too much off center. But anyway, you get the idea. This is the center. So the cube root of z third. Remember, they are separated by 120 each. Alright? Separated by 120 each. But this angle here was 100. So it's off like that. Alright. So therefore we have the 3 cube roots right there. Right? So the angles are 100, 220 and 340. Now the thing is, what else they asked us to do? What was the question again? Oh, the natural logarithm of z, right? We're supposed to find the natural log of z. We write it in exponential form. Z equal re to the j theta. Well, let's use I since the question has I to the I theta. Now, the original, this is the original polar form we're going to use. So 2, r is 2, theta is 300, r is 2, theta is 300. But remember now, when you're going to write it in exponential form, find the log and so on, you use radians, not degrees, alright? So, in degree, remember, 360 degrees is equal to 2 pi radians, so 180 degrees is equal to pi radians, so 1 degrees pi over 180 radians, so 300 degrees is pi 300 over 180. All right. Cancel for 30. Suppose you divide 6. 6 to the 35, so it's 5 pi over 16 to 18, 3. Right, 5 pi over 3. So it's 5 pi over 3 in there. Radians. So here z is equal to 2 e to the I 5 pi over 3. Now the natural logarithm ln z is equal to ln of 2 e to the I 5 pi over 3. Now you have the rules of logarithm, or the laws of logarithms. It tells you that this is ln 2 plus ln e to the I 5 pi over 3, which will be ln 2 plus, if you multiply by the power, I by 5 pi over 3 ln e, but ln e is 1. So this is ln 2 plus, I call it 5 pi over 3 I. Okay? If you should write this out in decimal, what would you get? Put in radians from now. Alright, so 2 ln would be 0.693. So you have 0.693 plus, and then you go to 5 pi over. Oh, I put in from degree to radian. I didn't do that because I'm not going to find any sine, cosine, tangent, or anything like that. It's going to be pi times 5 equal over 3 equal 5.236. 5.236i. Okay, so you have that. So in that case now, that's what you have. You could leave it in third form like this. So that is the natural logarithm of the complex number z.